What's going on? This is SDG Labs. My name is Anastasio Dalde. Let's do some math! Alright dudes, here's what we're going to be covering today. We're going to be covering domains, and here's kind of an idea that I wanted to talk to you guys about. Let's take a look at three functions right now. I'm going to take a look at y equals x squared. Alright, that one right there is basic quadratic. You got a graph that kind of looks like this. I hope my pen works a little bit better. Alright, there we go. There we go. It's a quadratic equation. Boom. Alright, and another graph I'm going to do is y equals the square root of x, which that one looks like this. Just making that small change right there. That graph looks like this. Y, x over here, this would be the y-axis, the x-axis. This one looks like this. I'll be honest with you, it almost looks like I took this parabola and then flipped them horizontally. Alright, here's the thing about domains. When I said whose domicile, our domicile, I got that actually from when I went to college. I was going to the school called Berkeley, and they had this commercial. It's hilarious. But they're talking about whose domicile, it's our domicile. Whose house is this? It's our house. It's one of those football things. Who's going to protect this house? All that kind of stuff. Anyway, it's crazy. But here's what the idea behind it is it is basically talking about, are you going to let somebody come into your house and mess with your stuff? You know what I mean? And in math, when I heard that, I thought to myself, okay, wait a second. Domain in math basically means what is allowed inside of your house. What is allowed inside of your function? And by allowed, I mean what is allowed to be inputted into your function. So we talked about the x-axis, and what a function is the y-axis actually depends on the x-axis. I can tell you exactly how high up to go depending on which x value you give me. See? X over here, I'll tell you have to go this high. X over here, I'll tell you have to go to this high. X over here, I'll probably tell you to go off the screen and whatever. Just like this one, you tell me an x over here, I'll tell you have to go to that high. So this y value depends on this x input. But there are restrictions to the input. Now for this particular function over here, there are no restrictions. You can tell me any x and I'll give you any y that comes out. You can tell me x equals negative 4,972. So that would be way down there, and then the x value would be some, or the y value would be some astronomical number up there. You could tell me x equals positive 3. Well, then there, and then, you know, positive 3 squared is 9. All right, we're good. This one, however, has a problem with the domain, because notice how I drew the graph. Now, you won't know the graph off the top of your head as soon as you see the equation. So what we're going to have to do is kind of do it more, approach it more mathematically. The way I drew this graph is, if you look at it, I only drew x for positive values. And that's because the x values that this thing can only be positive. Because you can't put negatives in the square root. So for this particular function, negatives are not allowed. Because if I asked you what is the square root of negative 4, the answer is, I don't know. Like if I asked you what is the square root of 4, you would tell me, oh, that's equal to 2. Because 2 times 2 is 4. It's also equal to negative 2. But if I ask you what is the square root of negative 4, you would say, well, I don't know how to do that right now, because if you're only considering what we call real numbers, let's see, positive 2 times positive 2 will give you negative 4? No. All right, what about negative 2? Negative 2 times negative 2 will give you negative 4? Also no. So I guess the question was asking, what times itself gives you negative 4? And the answer is, there is no answer. There is nothing that times itself will give you negative 4. So what you do is you say, all right, well, negatives are not allowed as x. X can be anything except a negative number. So we've kind of set the domain for that as x such that 0 x infinity. So this is saying x is in between. This is the answer. The domain for this thing is what's allowed to go into here. Well, that's between 0 and and infinity. X can be any number in between 0 and infinity. This is called set notation. It's x such that x is between 0 and infinity. Another way to write that in interval notation would be like this: 0, infinity. The reason why I put a bracket there is because you're allowed to have 0 as a part of your function. All right, now going back to this one was pretty straightforward. You can have any number, so it would go from negative infinity all the way to infinity. Or in set notation, it would probably look something like x such that x such that negative infinity is smaller than x is smaller than infinity, close that curly bracket as my set notation. I accidentally put a less than or equal to sign. There's no such thing as being equal to when you're dealing with an infinity. So it's just x is in between negative infinity and positive infinity. For this one, we consider it, another way to write it, a third way to write it is a capital R with a double line right there, which means all real numbers. So this domain is all positive numbers. This domain is all positive and negative numbers. All right, the last graph I want to show you, the last equation I want to show you is this one. Try this one out for size. Y equal to 1 over x. All right. As this graph gets really, really big, as the numbers x get really, really big, what happens to the value of y? Well, if I take a number 1 and I divide it by a really, 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 really big number, what happens is I'll get that x is equal to, or y is equal to a very, very, very small number, because 1 over 100 is small. 1 over 1,000 is even smaller. 1 over 1,000,000 is even smaller. So as I get further and further out that way, I'll get smaller and smaller and smaller. The graph will be. Now, if we set x equal to 1, what would be, okay, well 1 divided by 1, that's just 1. So the graph kind of looks like this. It's going to taper off over here. Because any number bigger than 1 would cause this thing to be a fraction, or a decimal point. All right, now what if we had 1 divided by 0.5, or, which is the same as writing 1 divided by 1/2, which is the same as just writing 2. Because 0.5 goes into 1 2 times. All right? So at x equals 0.5, you get a half, you get 2. At x equals 0.25, you get 4. So the graph's going to kind of go up like this. So this is how my graph's going to look. It's going to be a one heck of a roller coaster ride. You just kind of go over here and go, whoa! Got it? Same thing's going to happen for the negative, is only this time it's going to be on, negative. So the graph will look like this. But there is a domain problem here. As we get smaller and smaller and smaller, this y value is going to be bigger and bigger and bigger. It's going to go up and up and up and up. But I can't tell you what would happen if I put 0 in here, because I don't know, because you can't divide things by 0. The problem is things just explode. They literally explode. I guess one way to think about it is how many like if I had a piece of paper, let's use this one. I ripped it in half. And I said, how many half sheets do I need to take to fit in one sheet of paper? Okay. Well, I would need 2. All right, well, then I ripped that in half. Okay. How many quarter sheets does it take to fit in one piece of paper? Well, that's 1, 2, 3, 4. All right. This isn't 0. Let's get it smaller. See this? This right here? How many of these things does it take to get into one piece of paper? I don't know, maybe 100. You put 100 of these things together, you make one piece of paper. But this isn't 0. I haven't made it small enough yet. So I'm ripping off a fiber. I don't know if you can see the dust. In fact, let's go even further, and I'm going to take out my super micro tweezers and take off a single atom. There we go. You see that? In fact, I'm going to cut that atom into its protons and neutrons. So there we go. There we go. There's one proton of that piece of paper up there. In fact, let's even go down to quarks. All right, there's one quark of that piece of paper. That's not 0 yet, but it's really, 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 really small. So how many of those fit inside of a piece of paper? Oh, uku plenty, super million, billion, 100,000 kind, uku plenty stuff. Yeah, exactly. It gets super huge. So you can't go to 0 because I haven't even gotten to 0 when I talk about like 1 proton. So when it goes to 0, this thing explodes. So that's outside of the domain. The way we would write the domain of this particular function right here is we would say, oh, okay, wait 1 second, sorry. X such that x is not equal to 0. Because x is not allowed to be equal to 0. All right, those are the 3 functions I want to demonstrate for you. Shoots, bro, up out.